This is the Earth Science Classroom. Welcome back to the channel. This video is a combination of oceanography, plate tectonics, and wave physics. We're looking at how a tsunami forms. In this video, we're discussing what a tsunami wave is compared to other waves and how this wave propagates and what happens when this tsunami approaches the coastline. This is the Earth Science Classroom. Welcome back to the channel. This video is going to discuss how a tsunami works, including the ocean physics in terms of the wave energy, the oceanography, and the effect of this when these waves approach the coastline. Now, when you think of a tsunami, you think of a wave. Now, the most famous wave is the Great Wave painting by a Japanese artist in 1831. It depicts this very angry large wave destroying and causing issues with the Japanese coastline, with Mount Fuji in the background, and the fishermen's boats in the ocean. Now, this painting is really not far from the truth and what really happens along the coastlines when a tsunami approaches. A tsunami is a type of ocean wave, and an ocean wave is produced or formed from the energy that moves through this liquid. So if we're going to discuss energy, we have to look at wave physics and look at initially still water level and then add in what the energy of the wave looks like as it passes through the water, in this case the ocean. Now, the movement of energy is called propagation, and we see it's moving to the right in this diagram. And we add in the wave energy, we have the wave crest and the wave trough, which is the high point and low point, and then the distance between the wave crest and the next adjacent wave crest is called the wave length, or L, which the symbol lambda is used for. And we also have the wave height and the amplitude, which corresponds to the energy within the wave that creates the height of the wave crest from the still water point. And we also have the wave period, which denotes time, and it's the time it takes the energy to pass a fixed point through one cycle. So from wave trough to wave crest to wave trough, that will be the wave period, and that one complete cycle past a fixed point. And we can also include in this diagram of wave physics is the wave frequency, which is the amount of wave cycles that are passing a fixed point. So it's basically the wave period over a longer duration, which gives you the amount of waves passing a fixed point. And this can indicate the amount of energy the wave is carrying based on the same amplitude or wave height. So we discussed the basics of wave energy and how energy moves in terms of a transverse wave. Then we add in longitudinal energy or dynamics, which means that when you combine both of these behaviors of waves, they become orbital. And that is what the energy behaves like in the ocean, is orbital or circular motions through the particles, through the ocean. Now, ocean waves are divided into three different types or classifications based on the depth of the water the energy is moving through and the wavelength of the energy. Now, this is based on the wave base, the point within the ocean at a certain depth where the energy is negligible. You don't really feel the energy, but above the wave base, between the wave base and the ocean surface, you would experience and feel the energy as it propagates across or through the water. So the wave base is very important. The wave base is split into three different types. There is deep water waves, there is intermediate or transitional waves, and there are shallow water waves. The deep water waves are where you have the wave base, or the depth in which the energy goes down to within the ocean, is half the length of the wavelength. So if you have a wavelength of 10 meters, then the depth of the energy going down would be 5 meters. Anything below 5 meters, you wouldn't really feel the energy. Then you have the intermediate or transitional wave, which is basically a fluid, very large continuum of energy between deep water and shallow water. Intermediate or transitional waves have an energy size or depth which is smaller than half the wavelength but greater than 1/20th the wavelength. And this can vary based on the wavelength and depth of the energy as it moves through the ocean. Then we have shallow water waves. Now this is where the energy is at the surface but goes down through the entire water column from surface down to the seabed. Now these waves are important because tsunamis fall under this classification of a shallow water wave. So these shallow water waves have a energy depth less than or equal to 1/20th the wavelength of the energy. And the resulting behavior of this energy as it touches the seabed or ocean floor is that the energy or orbital or circular motion of the energy particles as it's flowing or propagating through the ocean is going to be affected by friction and contact with the ocean floor or seabed, and making these orbital energy motions flatter and more elliptical. And it's the friction and interaction with the ocean floor that's going to affect the particle motion within this shallow wave behavior. So we established the three types of waves. We have the deep water wave, the intermediate or transitional, and the shallow water wave. And we know that a tsunami is a special kind of shallow water wave because of its extremely large wavelength. In some cases, they can be up to tens or hundreds of kilometers wide from crest to crest, which means that with a ratio of 1:20, making it a shallow water wave, which usually exists around the coastlines in much shallower water, the energy in this tsunami is going to extend from the surface down to the ocean floor or the seabed, and that could be thousands of meters deep. But because the wavelength is so large that when you still divide by 20, you still get a very deep amount of energy that is propagating from the surface down to the depth. So the wave base is in some cases even beyond the ocean floor and seabed. So that's where you get the friction and the interaction between the wave energy of a tsunami and the ocean floor. Because the average depth of the Atlantic is around 3,600, and the deepest ocean on average is the Pacific, around 4,000 meters. So if you have a large wavelength, the energy is going to move through the entire vertical water column of the ocean as it propagates towards a coastline. Now, when it does approach a coastline, obviously the ocean water becomes shallower. The depth decreases, and the energy of this tsunami must go somewhere. So you get increased shoaling and friction between the energy of the tsunami as it's propagating through the ocean and the ocean floor seabed. And this creates a slowing down effect of the water. The water by the surface is still moving quickly with less friction and less interaction. However, the depth still is decreasing, and the ratio still becomes 1:20. It's still a shallow water wave, which means that the energy as it approaches the coastline must go somewhere, and maybe a small percentage may naturally flow into the crust, the ocean floor, the rock. However, the majority, if not all the energy, is kept in the ocean and creates an effect on the ocean surface. That effect is to push the wave height up exponentially as the wavelength decreases, as the energy and frequency continues to push in towards the coastline. The ocean wave height becomes exponentially higher and taller, to a point where the wave height versus the wave length makes the wave spill over and break, which is called Mitchell's limit. It's 1:7, so the wavelength to the height, and this wave is going to break and become unstable. So the energy is squeezed from the deep ocean as it approaches the coastline, and then the energy is dissipated as the tsunami is going to flow over the continental shelf and flow onto the shoreline, the beach or the coastline on land, and then eventually through gravity and gradient flow back to the ocean. So far we discussed wave energy, the types of ocean waves, the fact that a tsunami is a special type of shallow water wave, and how this shallow water wave extends through the entire water column of its energy and then propagates towards the coastline. What we haven't discussed is what natural phenomena initiates a tsunami. So what causes a tsunami? Now, one mechanism that forms tsunamis or seismic sea waves is subduction and the stick-slip mechanism, whereby friction occurs between two tectonic plates in a convergent plate boundary where one plate is subducting under the other due to slab pull and density differences and gravity, and the lighter, more buoyant plate on top is going to be dragged down with the subducting slab, and then over a certain time, the stress buildup and energy buildup within the rock and the contact and the friction gives way, and one side of the plate is going to snap back according to the theory of elastic rebound theory and cause large water displacement. This displacement is going to basically travel through the ocean as a shallow water wave, a tsunami, and impact the coastline as seen in this animation. In addition to plate tectonics, convergent plate boundaries, and subduction zones, tsunamis involve large volumes of water displacement over a very short period of time. Other causes could be landslides, volcanic eruptions, or meteor impacts. Extraterrestrial rocks striking the Earth's surface on the ocean and causing large water displacement. And the most famous example was the KT extinction around 65 million years ago, where the Chicxulub meteor, which is around the size of Manhattan, about 7 miles long, smashed into the Yucatan Peninsula off the coast of Mexico, in the modern-day Gulf of Mexico. That would have caused a fantastically large tsunami, one we have not witnessed ever by human eyes, and would have impacted North America, Central America, South America, Europe, and Africa. This is the Earth Science Classroom. Thank you for watching the video. I really appreciate it. And if you get a chance to like and subscribe, that stuff really helps the channel. Thank you so much. And see you again in a future video.